Okay, so what I want to tell you about functions and graphs, so what I want to just make sure that you understand is that when we have functions and graphs, functions have four representations. Okay, so if I have a function is a relationship. Okay, it's a relationship between an input and output. And a function, specifically functions, have for every input, one input can only have one output. Can only have one output. Okay, so if I talk about input, I'm talking about x values.
Okay.
So for every x value, I can only associate one y value with that x value. Okay. Now it doesn't mean that there is, so for example, I can have x value when x is 1, y is 4. When x is 3, y is 7. So when x is -2, y is +1. Okay, so there's for every one x there's one y value, and then it's called a function. Now let me take a different example, x and y. So let's say x is equal to 2 and then y is equal to 3, or x is equal to 3 and then y is equal to 8, or x is equal to -1, then y is equal to 0. I'm going to show you the relationships just now. X is equal to -2 will also be associated with x is equal to y equal to 3. So what I want to show you is every x value has only one y value, but there might be two y values that have different x values. So one x value can only have a single y value, but different y values might have, the same y value might have different x values. Okay, so how I like to explain it is like children and their dads. Okay, every child can only have one dad, but different children can have the same dad.
Yes.
Do you understand? So a father might have more than one. It should be like this. A child can only have one father, but the same father can have more than one child. Do you understand? Now that's the same with a function. The children are the x's and the fathers are the y's. So to say is something a function, it's literally asking who's your daddy. Okay, if every value only has one y value, then that's a function. Okay, so the next thing about it is that we get four types of representations. Now, what I mean by that is this relationship is expressed in four of representing. This relationship can be represented either by a table, and that's what we have here. These are two tables describing two different relationships. Okay, so a table or a function, or let's say a formula. So formula can also represent the relationship. So for example, in this case, my y value is taking my x value plus 3. Look there. So 3, then this one was 6, supposed to be 6, sorry. So taking my x value plus 3, so 3 plus 3 gives me 6, 1 plus 3 gives me 4, -2 plus 3 gives me 1. Okay, so this is a different way of representing the same thing. Here is another way of representing this one is by saying the y value is taking the x value, squaring it and subtracting 1. Okay, so 2 squared minus 1 is 3. 4 minus 1 is 3. 3 squared is 9 minus 1 is 8. 1 squared, negative 1 squared is 1 minus 1 is 0. Negative 2 squared, and that's where we see, okay, here we have two different x values, but they've got the same y value, because when I square it, the negative doesn't make a difference. You see? So that's why we can have, okay, so these are, that's another way of representing it. The third way of representing it is with a graph. With a graph. So, for example, let's do this. No. So for example, this first one I had 1, 3, negative 2. Okay, when x was 1, my y value was 4. 1, 2, 3, 4. Okay, when x was 3, my y value was 6. And when x was negative 2, my y value was 1. So look, I go up to the position where it should be. And this one, when x was negative 2, my y value is 1. Now you'll notice that based on a certain form, this one has a form, and we call that the straight line or the linear relationship. And a linear relationship looks like this. I like to use y is equal to ax plus b. Okay, that's the linear relationship. So we call it linear because when we represent it on a graph, all the relationships will, if I plot every single point, they will all plot on a straight line. Okay, that's why it's called linear. This one is called the quadratic relationship because the relationship has that square in it. Okay, so if we draw the quadratic relationship, okay, for example, so for example, we've got when x is 2, y is 3. So when x is 2, y is 3. When x was 3, y was 8. 3, y was 8. When x was 4, negative 1, y was 0. When x was negative 1, y was 0. Okay, when x was negative 2, y was 3. When x was negative 2, y was 3. And then if we were to draw this one, we would see, if we did all of the possible values you can imagine, whether it's 2.5 or anything, we see it makes a shape like that. Okay, and now we can see why, for this one for example, we can see why it's a function, is because when we draw a vertical line up, okay, we will only cut our graph once. And when we draw a horizontal line, we will only cut our graph once. Now this one, if I draw a vertical line up, I will always, no matter where I draw this vertical line upwards, I will always cut it only once. You see, that's when it's a function. The difference is this is a one-to-one function. The one-to-one function means that I've got for every x value, one y value. But I've got also for every y value, one x value, while this one is not one-to-one. This one is one to many and many to one. Okay, so in other words, this one, if I draw a vertical, horizontal line, notice it cuts twice. That is called that is then not one-to-one. It's still a function, but not a one-to-one function. Make sense? Okay, cool. Now, what else? The fourth representation is describing it in words. So I'm not going to write that down. That's just like saying whatever you give me, I'll add 3. That's saying this in words. Whatever you give me, I'm going to add 3. Okay, that's a fourth representation. We don't really use that much in maths, but it is what we'll, often with word problems, we have to get from the wording into a math expression. Make sense? Okay? So those are the 3 types of ways we're going to work with. This method, we very seldom use it because it eliminates a lot of relationships. Here, I only have 3 values represented, 3 inputs represented. While in the formula, you can give me any x value, and I can give you the y value. While in this table, you have to give me one of these values for me to give you the y value. Do you understand? So it's very seldom that we use the table. The graph and the formula is much more convenient, because if you tell me, well, what will the y value be if, or what will the output be if the input is 7? Then I go on my graph to 7, and I go from there up until I cut my graph, and then I go sideways to read off what the y value would be. Do you understand? So that's the very important relationship between the formula and the graph that we must focus on. But let's now, for now, go and look at the different graphs that we're going to work with. Okay? We're going to work with the straight line. Straight line. And his general formula, the way I know that the formula will draw as a straight line is it will look like this. I'm going to go with the ax plus b. Ax plus b. We'll look at the detail of each of them just now. The straight line, the parabola. Okay, parabola. I'm sure you know all this. Ax squared plus bx plus c. Okay, this is just the graph that's associated with the formula. Okay, the hyperbola. Is y is equal to, now hyperbola, at school level we only do one type of hyperbola, but the type that we do looks like this: x minus p plus q, and we'll explain what each of these values are, and then we'll do the exponential function. The exponential function. Okay, and we also do, I don't have space here, the logarithmic function. Logarithmic function. These two are very closely related to one another. Okay, so the exponential function looks like this. It's y is equal to a base and an exponent. So notice here, what makes something linear is that the x's highest exponent is a 1. What makes something a parabola is the x's highest exponent is 2. What makes something a hyperbola is that the x is somehow his exponent is -1. Okay, he's in the denominator. What makes something an exponential function is x is the exponent. Does that make sense? What makes something a logarithmic function is y is the exponent. So logarithmic function looks like this. Y is equal to, let me stick to my colors. Y is equal to log, well, not bog, log base exponent. But if I rewrite this into an exponential form, that's the same as saying base with y as my exponent is equal to x. So notice that y is the exponent, and that is why the exponential function and the logarithmic function is very similar. The only difference is x and y has been turned around, and these are then called the inverse. The inverse. Okay, and as a result we also work with the inverse of the parabola. The inverse of the parabola is called the root function. a root function. And the root function looks like this. Y is equal to the square root of ax. Okay. Now, again, how do I know something is a parabola? I know it's a parabola when the x is squared. When is something a root function? It's when the y is squared. Because y squared is equal to ax. Notice that. Okay, so again, these two are each other's inverse. Now, the root function, or the inverse of a parabola, is not a function. Because a parabola looks like this. The inverse means I flip it around the line y is equal to x. I change my x and my y values. So the inverse function will look like this. Now, or the inverse will look like this. Now it's not a function anymore. Because when I draw, for every x value, there's now 2 y values. You see that? So there's something special that we need to do first before we can get the inverse of a parabola, so that the inverse is a function. Okay, but we'll look at that just now. When we draw a function, drawing function, the first thing I want is the shape. I just want to know, I have to draw this thing. First thing I need to figure out is, what does it look like? What shape does it have? So let's go and look at each one's shape. Straight line, no problem. Very few people have a problem with the straight line, and yet they do have a lot of problems with straight line. I don't get it. Anyways, but straight line is just a straight line. A straight line doesn't have to look like this. They might give you a straight line like this. They might say 2x plus 3y is equal to 7. Is that a straight line?
Yes.
Yes, because my x's exponent is a 1. Okay, so that's a straight line. I just need to write it in that format first. Okay, so that's straight lines. Parabolas, we've looked at that now a few times. We looked at the parabola, looks like this. That's the shape, or the shape is like this. Same with the straight line. The shape is like that, or the shape is like that.
Yes.
Okay, but it's a straight line. Parabola has this smiley or frowny face. How will I know? Okay, the way I look at it is I see this one is, he ends up going up. You see, he ends up, in the end, if I walk on this one the way that I read, I'll end up going up, which means it's a positive shape. This is the negative shape, because if I walk along this one, I'll end up going down. Okay, now A determines that. The value that's in front of the x determines whether I end up going up or end up going down. If that value is positive, if A is positive, I end up going up. If A is negative, I end up going down. Okay, I'm talking quick. If I'm losing you, you'll tell me. Oh, okay, so I want to get through this quick because I think you get most of this. Okay, now this one, same thing. Here I end up, if I walk here, yes, I'm going down, but I'll end up going up. Here I'll end up going down. At some point, if I walk, I'll go up, but I'll end up going down. Okay, and so this is the positive shape, sorry, the negative shape. In other words, when the value in front of the x squared is negative, then I know I've got this frowny face. If it's positive, I've got this smiley face. Okay, the hyperbola is slightly different. I look at it differently. There's two shapes that it can have. It can either look like this and that. It's got two parts. It's one graph, but it's got two parts. Okay, and now for me, what I like to do is I look at or this is how I remembered at school, which is the positive or which is the negative shape, is if I connect these two, you see, if I kind of connect them in my mind, it has a positive shape like the line, the straight line. Do you understand what I mean?
Yes.
Okay, while the other shape would look like this. Now if I connect these two in my mind, they will have a negative shape.
Oh, so you're looking at the line you constructed, and then from there you say, am I going up or am I going
Exactly, yeah. Yeah, that's exactly what I'm doing. So I'm kind of just in my, there's not really that line. Okay, I'm imagining I'm connecting them with some sort of line, and then that line, if it's positive, so this is the positive shape, if the A value there is positive, and that's why I want to use an A here, because I'd like to think of A as the form constant. Okay, so if A is positive here, if A is negative, it gives me the form constant. It will be in the two, I call it the two negative quadrants, and the reason why it's negative quadrants is because the first and the third quadrant is positive.
Okay.
The reason why is because a positive and a positive is positive. A negative and a negative is positive. You see, that's why that's literally the reason why the one graph is here and the other graph is there. Because if A is positive, then these two values, the x's and the y's, must multiply to give me positive. If it's negative, if A is negative, and why do I say x times y? Because look here, y, if I multiply everything with the denominator, then on this side I got x minus p. So x times y is important in this case. So if x times y is positive, it means, so we get that answer A. If I multiply this on both sides, plus the q thing, but ignore q for now, okay, the A value, if A is positive, it means y times x must be positive. So y times x must be positive. So y times x is either in this quadrant or it's in that quadrant. Okay. Same with if A is negative, it means y times x must be negative. So either y is negative and x is positive, that's in this quadrant, or y is negative and x is positive, that's that quadrant. Make sense? Okay. Moving on swiftly, I forgot to mention the rest of the parameters. Now, parameters are these values. It's the values that's not x's and y's. Parameters are literal values. It will be like a 2 or 7 or 1 or -5. Parameters are these values, the a and the b, the a, b and c, the a, p and q, the b. For the exponential function, he's actually the most difficult in terms of parameters. We've got a parameter in front, I like to call it c, okay, for coefficient. I like to call this one b for base, so it's a little bit different than the a's in the past. B's for base, and then we get plus a. I use an a here, and this a, I call it a because I like to think of it as the asymptote.
Okay.
So we'll look at some examples and then you'll understand why I call these CB. And then there might be a plus or minus P up here, which moves the graph left or right. Very seldom that they do it, so I'm not going to focus too much on it. For the logarithmic graph, obviously it can have the same thing, because this graph can, the x value can be expressed as that as well, but that we will basically only work with the normal logarithmic graph like that. And all you need to know is that if my graph moves left or right, I'm adding or subtracting from the x value. But we'll look at an example just now. Okay, so let's quickly look at the way that we're going to draw. We said the shape. Now, I didn't look at this one shape yet, sorry. The shape for the exponential function, there's 4 shapes for the exponential function. Very important that you know those 4 shapes. Okay. It's not very difficult if you understand what C and what B does to the graph. Okay, so the B value for my exponent, for B is my base. My B value can never be negative or 0. So you will never have a negative base. If you have something like this, if you have something like y is equal to negative 2x, the negative is not part of the base.
The negative is the coefficient.
The negative is the coefficient. It's actually negative 1 times 2 to the power of x. The negative 1, the base itself is that 2. Okay? If it was like this, you go and try and draw a graph like that. It's a ridiculous graph. It's like little dots like all over the place. It's because each time, if x, for example, is a half, then you have the square root of negative 2. Because if my exponent is a half, then I'm working with a root. If x is something like a negative value, then all of a sudden I'm working with a fraction. So this thing it just doesn't work as a graph. As a matter of fact, I don't even know what it will look like if you try and plot it. Anyways, so we don't have, our base will not be negative, but my b can be either smaller than 1. It can also not be equal to 1, because 1 to the power of x is always 1. So if it's equal to 1, it will be a horizontal line. If my base is equal to 1, so you will never get that. Okay, if my base can be either greater than 0, I just told you it can be greater than 0, or less than 1, then it will have a specific shape.
But if it's greater than 0 and less than 1, that means it's your 0.5.
Yeah. In other words, it's a fraction. It's a fraction less than 1.
Okay.
Now you can have, I didn't say your base is not allowed to be a fraction. It's not allowed to be a negative value. Your exponent can be anything. Because what am I not allowed to put for an exponent?
So the exponential function.
No, in x there. What am I never allowed to put in an exponent?
0.
Of course you can put 0 in an exponent.
Yeah,
When I put 0 in, I get a 1 as an answer.
Yes.
So I can put anything. For exponent I can put anything. Okay? So what I'm never allowed to do for a base is a negative value. So for example here, inside here, I'm limited to what I'm allowed to give x. I'm not allowed to give, well, it depends what a is. If a is positive, x must be positive as well. If a is negative, x must be negative as well. Because I'm never allowed to get a negative under the square root. So here I'm limited. In the exponential, in the straight line function, am I limited for x? No. So this is what we're talking about domain. What am I allowed to put in? In this case, I'm allowed to put in anything. So I'll write x as an element of real numbers. In the parabola, what am I allowed to put for the base of a positive exponent? So now, is there anything you're not allowed to square? No. So x can be any real number. How about here?
No, I don't think you are limited, because if x is negative, your amplitude is going to be negative, which you can draw. So I don't think you're limited.
Okay. There's two limiting factors. There's only two things in high school maths, or when we work with real numbers. In high school we only work with real numbers. There's two limiting things in real numbers. One is I cannot have a negative under a square root. That's not real numbers. That's imaginary numbers. Okay, so that was the one limiting factor. The other limiting factor is I'm never allowed in any number system to divide with 0.
Yes, because I forgot about that.
No, that's okay. That's okay. But that's now the only. So here, what can x not be?
0.
Oh, x can be 0.
Because we have a p.
We have
so
a p.
0 minus p can give us an actual
Can give us an actual value. So what can x not be?
The opposite. If p is minus 2, then x cannot be 2.
Exactly. So x cannot be equal to p.
Yes.
Because otherwise I'll have p minus p.
Which is going to give me 0.
Which is poo. So x is not allowed to be p. X can be anything. So we write x is any real number, but x cannot equal p. Make sense?
Yes.
Okay, so this is my domain. Here, what am I allowed to give for an exponent? We talked about it earlier.
Yes. Isn't it any number?
Any number. So again, my input value is any number. Any value that I can put for an exponent is nothing. Here, again, I'm looking at limiting factors. I'm not allowed to divide by 0. Well, there's no dividing happening here. Okay? And I'm not allowed to have a negative under a square root. Okay? But x is not in a square root. X is not in a denominator. Does that make sense?
Yes.
So I am allowed to put anything there. So it's only square roots and denominators that's going to limit me for my input. The output is a different story. So this is called the domain, is what am I allowed to put in. Okay? So far, in the log. Okay? The log, okay, I said there's only 2 limiting factors. There's 3. Okay? But it's yes, okay, there's 3, I lied. There's 3 limiting factors. The one is if I have a denominator, then my denominator may not equal 0. The other one is if I have a square root, then my x must be greater or equal to 0. I am allowed to have a 0 in the denominator. But with a log, if I have an input in a log, I must be greater and not equal to 0.
Yeah.
Okay.
Negative numbers have some math error when it comes to log.
Is that why we're not allowed to put it in?
I think so.
Because the calculator says so. Okay, let's quickly see why is that. Okay, so notice that we rewrote this one, we rewrote it like that. Now we are saying that x may not equal negative or 0.
Yes.
Let's see if that's possible. Remember, b is not 0. b is not equal to 1. b can be any other number. Okay, so if x is negative, what is happening on this side to give me a negative answer? What exponent, so remember, b cannot be negative.
So that means the exponent is not
What does a negative exponent mean?
divide.
Divide, does it change the sign at all? So for example, if I have 2 to the power of negative 1, that's just a half.
Yes.
It didn't change the sign of the value.
Okay.
It's impossible. If my base is not negative, no matter what I do to the exponent, I can't get a negative answer. Because the exponent just tells me what times what, how many times do I multiply, or how many times I divide. Okay, so it's impossible. Okay, let's say, what exponent must I give a base in order to get 0? In other words, I said x is greater than 0. In other words, it can't be negative. But why can't x be 0? What exponent can I give a base to get a 0 answer?
No.
Nothing. It's impossible. No matter what I do with my exponent, if I give it a very large negative number, like for example 2 to the power of negative 200, that's very close to 0. That's almost 0, but it's not. You understand? It's taking 1 and dividing 1 with 2. So in other words, I take a cake and I divide that cake in half. Then I've divided it once. Now I take that half and I divide it again. Okay, now I've got a quarter. Now I take that quarter, I divide it again. If I do that 200 times, how big is the piece going to be? Okay, it's too small. I want the rest. Okay, so it's very small, but it's not 0. No matter how many times I divide it, it can never be 0, because when I put everything together, I must get the whole thing again. Make sense? Okay, so in other words, it's impossible. I can't get 0. So that's why in logarithm, my input is the answer to b to the power of y. So my input is literally asking b, what exponent must I give you to get y? So, sorry, what exponent must I give you? So something like this, log of 8 is asking the question, 2, what exponent must I give you to get 8? and 2 will say you must give me an exponent of 3. So now log 2, 0, we ask 2, what exponent must I give you to get 0? Undefined. There's no exponent I can give 2 to get 0, so this is undefined. So the domain for the logarithmic function is x is greater than 0. Make sense? Okay. So that is now domains. I was actually still busy long ago with showing you the shapes. So we were the hyperbola shape, okay, now the exponential shape. Now you'll see when I draw my graph, if my domain is all the values, I can draw the graph without lifting my hand. So look, I can draw the graph without lifting my hand. I can draw the graph without lifting my hand. Okay, and I can start, no matter how far back I start, I can draw it. The shape for the root function, okay, it does look like I can draw it without lifting my hand, but this is not a function. The root function, if I want to have a function, it will look like this. It will start there and go. So I can't start as far back as I want to. So I can't draw it without lifting my hand, no matter how far back or how far forward I start. I have to lift my hand and choose a point and start from there, and then it goes on. Here it stops. Okay, that's the root function, okay? This one, can I draw this graph without lifting my hand?
No.
I can't. I can draw this part, but then I have to lift my hand to draw that part. You see, which means it's not all the real numbers. As soon as it's all the real numbers, I can draw it no matter how far back I start, all the way up. Okay? Exponential function, doesn't matter where I start, I can draw it. So let me show you now the 4 shapes. So it will look like this and go up to infinity. Okay? This is the shape if b is greater than 0, but is greater than 1. Sorry, I said b can be, and I don't think I finished my word. B can be between 0 and 1, that will be one shape, or it can be greater than 1, it can't be equal to 1. Okay, so if my base is greater than 1, it will end up going up. If my base is smaller than 1, it will look like that. Okay, which means it will end up going down. Okay, now the other thing is this coefficient in here, what comes in front here. Now that is similar to these ones. What the coefficient in front of your x actually does is it flips it around the x-axis. If it's negative, it makes all the positive y values negative y values. You understand? So that's why these ones take that and it turns it upside down. Look, this one even. It used to be there and there, now I flip it in the x-axis, now it's there and there. Now that's exactly what the c does. The moment it's negative, if b was greater than 1, it would look like that, but now c is negative, so it will look like that. You understand? It's mirroring. It's mirroring in the x-axis. You see that? Same with this one. If b is smaller than 1, it will look like that. If I mirror it, there we go.
Okay.
You get it?
Yes.
Cool. And now the logarithmic function, we'll have to make some space for that. Okay, so our logarithmic function, it helps to understand that the logarithmic function is the inverse of the exponential function, because as you can see, if I change the x and the y values, then it's an exponential function again. So it's kind of helpful to then look at this as as my, this is now my y value, and then it is my x value, my x-axis, and now I'm trying to kind of draw this, but by swapping x and y around. So here you can see, if my base was bigger than 1, in other words, if my base is bigger than 1, then I went from where x is negative, I was close to the x-axis, and when x was positive, I was moving away from the x-axis, and I was on the whole time I'm on the positive side of the y-axis. So now I must just change all my words around. When x is negative, so when y is negative, when x is negative, I was close to the x-axis. So when y is negative, I'm close to the y-axis. So I'm here, close to the y-axis. When x is positive, I move to infinity. I go away from the x-axis. So now I must say when x is positive, when y is positive, I'm moving away from the y-axis. So this shape will look like that. See, it's the same shape, but just a little bit flipped around. Okay, and that goes for, again, my b will either be bigger than 1, then this will be the shape if b is bigger than 1, or my b will be smaller than 1 and bigger than 0. So if b is smaller than 1 and bigger than 0, then it will just be the opposite. It will be this one, which will again be, well, if x is positive, in other words, when y is positive, I'm close to the x-axis. I must be close to the y-axis. So this one will look like that. Okay.
Okay.
You get it? Not that bad. Okay, so that's drawing the graph. Now, what might happen is you might get a negative in front there. Now, what a negative does in front of the graph, what does it do?
Changes the shape.
It changes the shape, but what have we seen so far? How does it change it? A negative will always flip it.
On your
X-axis or y-axis?
Y.
X-axis, because all my positive y values will be made negative y values. So everything that used to be there will now be there. Now, so what it will do is y is equal to, let's say for example, negative log 2x. Okay. Now what it will do, that negative actually will just flip it around. So this will be the same as having a log of a half x. You see, because it flips it around. What used to be this one will now become that one. Okay, and there's a way, I suppose I can somehow find a way of showing it to you. So for example, this is the same as saying log of x divided by log of 2. Are you with me? Do you know your log laws?
Yes.
Okay, so if there's a negative, I can just, instead of putting my negative with my numerator, I can put it with my denominator. Now a negative in front of the log is the same as saying log of x over log of 2 to the power of negative 1. You know that log law?
Yes.
What's in front of the log can be the exponent of what's inside. So that negative 1 in front here can become there. But 2 to the power of negative 1 is a half. So log of x is the same as log of 2 to the power of negative 1 is the same as that. Now this, using the same principle where I split the 2, I can now put them back together again by saying this is log of a half x. You get it? It's okay, Nate? Okay, excellent. So I'm still here talking about the shapes. So those are the different types of shapes. So if they give me a function, that's the first thing I'm going to look at, is what is the overall shape? Is it exponential? Is it parabola? Is it straight line? Is it hyperbola? Is it root function? Whatever. Okay. The next thing I'll ask is, where should it have the positive or the negative shape? That's okay now? Okay. So that's the first thing. After we've determined the shape, we find the intercepts. And how do we find the intercepts? Always the same.
If you make x 0, you can get your y. And if you make y 0, you can get your x.
So we make our x, and so there's nothing you need to go and study. You don't need to remember which parameter. Remember, I called these ones parameters. You don't need to remember which parameter is the x value, which parameter is the y value. You just always do this. Okay, so there's so little study. All you need to study is the shapes. And then the rest, all you need to know is, well, my x-intercept is when y is 0, and my y-intercept is when x is 0. So if you want to go and draw these graphs, I need to know my shape. But now, for example, let's say they give me quite a challenging value like this. Y is equal to negative 2 to the power of x plus 3 minus or plus 4. Okay. Now they ask me to find the intercepts. Well, all I need to do is I need to make x equal to 0. And so I get negative 2 to the power of 3 plus 4. That is negative 4. You see that? Okay. If I need to take the y-intercept, I take 0, sorry, the x-intercept, I make y 0. So negative 2 to the power of x plus 3 is plus 4. Now I just solve. And negative 2 becomes positive 2x plus 3 is equal to 4, which means that 2 to the power of 2 equals 4. You get that?
Yes.
Would you be able to solve this?
Yes.
No, so x plus 3 must equal 4, so x must equal, sorry, 2. 2. X plus 3 must equal, so x must equal negative 1. So there's my two intercepts. Okay, so now already, look how easy was this. I can already go draw this graph because I know what is this, the positive, will this one end up going up or end up going down?
End up going down.
You are right, but I'm hoping now you're not making two wrongs. Okay, it ends up going down because of the negative in front. But because the base is bigger than 1, it actually looks like this. Okay, but because of the negative, it gets flipped around down. Do you understand that? Okay, but, so this is the shape. That's the shape. Now, based on the shape, I must go through the two intercepts. My y at negative 4, so I must go through negative 4. And my x must go through negative 1. Negative 1. So I must draw this shape through those 2 points, which isn't that difficult. Or I'll do, let's choose red. I must just make a shape like that. So here we go. We've done it. Okay, cool. The next thing after the intercepts, after I know the intercepts, I need to find the asymptotes. There's only 3 graphs that have asymptotes. Asymptotes. And those are lines that the graph tends to, but it never reaches it. Okay, so doesn't necessarily mean it doesn't reach it, but they tend to go towards it. Okay. In the hyperbola, we have a horizontal and a vertical asymptote. The horizontal asymptote is obviously the value that x cannot be, not the horizontal, the vertical one. Okay, x can never get to this p-value, so as it's trying to get there, it's being pushed away. From this side, it's trying to get there, but it's being pushed away. Do you see? So there's this one line, it's on the x-axis, that value is the one it tends to, but it never reaches. So there's the hyperbola. Hyperbola has a vertical asymptote x is equal to p. So this p value represents the vertical asymptote. The horizontal asymptote, let's quickly look at the horizontal asymptote. Before I do, let's quickly look at the range of functions. Now, the range is, if I talk about, if I wanted to throw a ball, my range is how far can I throw it. So my positive range would mean how far can I throw it forward. My negative range would be how far can I throw it backwards. Makes sense? Now in a graph, the range is all the outputs that I can possibly get, all the values that I can get. Now for a straight line, there's no vertical line, horizontal line, sorry, that I can draw that won't cut my graph. Does that make sense? So y values, every single y value that I want, I can get. All I do is I go to that y value, and then I go horizontal until I cut my graph, and then I go down. Okay? So a straight line, the y values, that's the range, is all the values I can get from this function. In other words, on this side, I can put any value and solve it and get an x answer. That's kind of what it boils down to, any value. Parabola? What do you think the range of the parabola? Is it the same? Can I get any value?
No.
Why not?
Because for every y value, you can have more than one x value.
Okay, but can I get that y value? Even though I've got two x values to get that y value, can I get, for every y value that you can imagine, you can find at least one or even more than one x values that will give you that answer?
I don't think so, because when looking at the shape of the parabola, it goes like that. So maybe, let's say the turning point is at -2, 0. The points below, -3, those y values, you cannot get your x values.
Excellent. So in the parabola, there's a different way of writing the parabola formula. If you complete the square, you can write it like this. You know that, huh?
Yes.
They call it the vertex form. In this form, P and Q is the turning point there. P, Q is the turning point. Okay, and you're exactly right. If I can only get y values, so my range is only bigger or equal to the Q, the turning points, the y value for my turning point, that's Q. I can only get it bigger or equal to Q if I have the smiling face. Then it will be bigger. If I have the frowning face, that one, I can only get the value smaller than Q. So I don't have all the values. Exactly right. Okay. Now if we go to this function, it also makes sense because x minus p squared is always positive. So I can't just put any value there. So for example, if I had y is equal to x squared, my turning point is 0, 0. Because there's nothing subtracted from the x, so p is 0. There's nothing added outside, so q is 0. So that's my turning point. It's positive, so my range is greater or equal to 0, based on what we described now. But it also makes sense because I can't put a negative value for y, because there's nothing I can square to get a negative value. Does that make sense? It's impossible to get a negative value if I'm squaring my inputs. Okay? Unless I subtract 5 as an example. Now I can get negative values, but nothing less than -5. You see, so what happened? My graph shifted 5 down. So now my turning point is 0, -5. Y is now greater or equal to -5. Because I've subtracted that 5, this part will always be positive. So the smallest value I can get is when I have 0 here minus 5. Makes sense, huh? Okay, cool.
So, quick question. You see with the range, sometimes on the program you write it as an interval notation.
Oh yeah?
Maybe you can say negative infinity towards the turning point, and then from the turning point towards the other infinity. So that's what I really don't understand with the range.
No, let's do the hyperbola, then you'll see what the range for the hyperbola. This one's range, even if we use interval notation, will be from -5 to infinity. There's not another point. So it's not like we have a range for this leg and a range for that leg. Both of these have the same range. Both of them go from -5 to infinity. But when we work with the hyperbola, we've got this leg going from 0 to infinity, and that leg going from 0 to infinity, negative infinity. And the actual point is that we can't get 0. Do you see? So it's not like this one we can't be less than 0. With this one we can't be equal to 0. So this one, for example, writing this range, this domain, to write this domain in interval notation, x can be all numbers from negative infinity up to infinity, isn't it?
Okay. Yeah, because it goes all the way down.
Yes, so it can, no, think about x, all the x values. I can have all the x values until I get here. Now I need to make a little bit of a jump. So until I get to my p value, I must exclude p value, but then I can again include everything after p. Do you understand that? So this is the way of writing this. All the numbers would be from negative infinity to infinity. But I must exclude p. So when I get to p, I exclude it by writing these two round brackets. One for when I get to p, and one for when I start from p. And then I just use this united to say that my x can be in either one of these two signs.
Okay.
Make sense? Now the same goes for the range of this one as well. Now let's just understand the range. If I tell you y is equal to 1 over x, what y value can I never get? We know x can never be 0.
Yes.
What can y never be?
Isn't it that y can never be negative?
Well, if x is -1, then it's 1 divided by -1.
Yes. So it can, because then if y has...
Now think of it like this.
Old number, then like it will always be a fraction.
If x is a half, then 1 divided by a half is 2. So think of it like this. A fraction, it's impossible for a fraction to ever be 0, no matter what I do in my denominator. Because, and I like the cake example, if it's my birthday and I bring a cake between just you and me, Pindile, and I divide it, you will get a half, I will get a half. So if I divide in 2, I get a half. If we divide by John, yourself, and me, we each get a quarter. It's now a smaller piece. No matter how many people I divide amongst, I will never have 0 pieces, because when I put everyone's pieces back, I must have my whole cake. Okay, now it's going closer to 0,
But
it's never getting 0. So that's why if we look at the graph for this thing, okay, as x gets larger, look, as x goes higher, initially there was just me. If it's just me, I get the whole cake. If it's me and Pindile, now if we're 2, we each get half. if it's me and John and you, Kundila, now each of us get a third. This is now a third of 1. Now, as we get bigger and bigger, this value gets smaller and smaller and smaller. Do you see?
Yes.
But it never reaches the 0 line.
Okay.
It cannot. Okay? Now, the same goes for the negative side. The only difference is now I'm just dividing with a negative 1. 1 divided by negative 1 is negative 1. 1 divided by negative 2 is negative a half. But the same goes, so I'm going to negative infinity. As x goes to infinity, y becomes 0, but it's coming from the negative direction. It's coming from negative 1, negative a half, negative a third, negative a quarter, negative a fifth, negative, it's getting smaller and smaller from the negative direction. Make sense?
Yes.
Okay, so a fraction, this fraction can never be 0. No matter what that fraction is, even it doesn't matter what I do in the denominator, if it's x, if it's minus p, no matter what, the fraction, the whole fraction can never be 0. Now, my general formula though, even if the only time my fraction can be 0 is if my coefficient is, my denominator is, numerator, sorry, is 0. A denominator cannot be 0. Okay? But if my numerator is 0, then I've got nothing that I'm sharing with you two, so each of us get nothing. So that makes sense, doesn't it? Okay, so plus p. So what, if the fraction can never be 0, what can this whole expression never be?
If the value of a is 0.
No, the value of a is not 0. That's what I'm saying. But I'm saying this fraction itself is impossible for it to ever be 0.
Yes.
So if I now add a p, what can this expression never equal?
P.
It can never equal p, because p can never be by itself. This can never vanish, it can never become 0, so I can never just have p. I will always have p plus a little bit. Okay, so y cannot equal p. So in this expression, in the same way that x can never equal q, y can never, x can never equal p, y can never equal q, because the fraction can never disappear. Make sense? Okay, so that would be my vertical asymptote. That's the y value I never reach. Okay, so my horizontal asymptote is y is not equal to q. Okay, that's for hyperbola. Then we have the exponential function. Now, in the exponential function, we already saw that x can be any value. I can put anything in the exponent. It's only when it's in the denominator that I've got a problem. But the y value, we have a problem now, because we saw earlier that, for example, with the logarithmic function, we saw with the logarithmic function that in this expression, it's impossible for this thing ever to be 0. And it's impossible for it to be negative as well. So even though it might come close to 0, it never gets there. And it comes close to 0 only when my exponent is negative. So, for example, if we look at this shape, this is typically something like y is equal to 2 to the power of x. So as x is getting bigger, obviously 2 to the power of x is getting bigger. That's like 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Okay, it's getting bigger and bigger and bigger. But as x is getting smaller in the negative side, now it is actually y is equal to 2 to the power of negative 1 is a half. 2 to the power of negative 2 is a quarter. So do you see, when my exponent is negative, I'm actually working with fractions. What can a fraction never be?
0.
0. So I can never get to 0. Even though I get close, the bigger my x becomes in a negative direction, the smaller my fraction is, but it never gets to 0. So if I have base exponent, what can this one never be? What can b to the power of x never be? Can't ever be 0. Okay? So, if I multiply this with a c, what can this expression never be? It can't be 0. Okay, but if I add an a, what can this whole expression never be?
Equal to a.
It can never equal a. Because this part can never be 0, so it will be always a plus something. So here we get that the exponential function only has a horizontal, it doesn't have a vertical asymptote because x can be anything, but it has a horizontal asymptote, x is equal to a. Okay, so in this one that we were drawing earlier, where's our, so all we need to do is, you don't even need to see which one is a. You can just see, well, what was it, that one actually? This base exponent thing, this thing can never be 0, so y can never be 4. So I will have a horizontal asymptote, y is equal to 4. Makes sense, huh? Okay, now the only other one is the logarithmic function. So there's only 3 functions with asymptotes. The other one is the logarithmic function, and we've already actually looked at its asymptote. Is that in a logarithm, we've got our base. This is not allowed to equal 0. So let's say they now go and they're funny and they give you a weird logarithmic function like log of 2x minus 1. What would the asymptote be? 1. It's x is not allowed to equal 1, so x equal to 1 will be an asymptote. Okay, so if I had to go and draw that thing, I would see here's my 1 asymptote, and I've got 2 which is bigger than 1, so it will have that shape where it, in the positive part, in the positive quadrant, it is going to infinity, while if it was a half, in the negative quadrant it would have been going to infinity. Okay. Shucks, I think that's it. And is it, oh, special points. Special points. The only graphs with special points are the parabolas. Parabolas, it's got a turning point. It's got a turning point, and that turning point we've already seen is the point P comma Q. Now if you have this format, that's very nice, because you can just get P and Q. If you have that format, you'll just need to use your formula, isn't it? P is equal to negative B over 2A. Okay, and then Q, you will take will be equal to your function, and you'll just substitute the P that you've calculated here, and then you'll get your Q value. Okay, so that's the special point for the parabola. For the hyperbola, we also have a special point. Hyperbola, okay, it also has a turning point, a special turning point that's not often mentioned. It's that point there. Okay. I can't remember what that point is.
Isn't it where your axis of symmetry lies?
It is. It is exactly where the axis of symmetry, the positive axis of symmetry, y equal to x, where that one cuts it. So what you could do, but this line is not always y is equal to x. Let me quickly think about it. Well, I tell you what you could rather do is, I'll get to that just now. The only one with special points is then the parabola. I didn't look at the cubic function yet, because I want to look at that when we do the derivatives. We'll look at that when we do the derivatives. But your special points is really actually so easy. Is all you do is you take the derivative and you make it equal to 0. Look here. Ax squared plus bx plus c equal, okay, this is my function, isn't it? This is f of x. Look what happens if I take my derivative of this and I make it equal to 0. That's 2ax plus b equal to 0. Have you gotten two derivatives yet?
Yes.
Okay. Now I solve for x. 2a is equal to negative b. Sorry, 2ax is equal to negative b. So x is equal to negative b over 2a. It always works. If you take your derivative equal to 0, you are finding the turning point. That's what you're doing when you make your derivative equal to 0. The derivative is a formula for the gradient. The gradient at the turning point is 0. So if I make my derivative, my formula for the gradient, equal to 0, I'm working out where is my gradient 0. Make sense? Excellent. So to find special points for a parabola, okay, hyperbola, I don't want to include it under here because it's not the turning point. So let me, instead of calling it special points, let's just call it turning points. Turning points. Okay, special lines, let me just look at special lines and that will be the end of it. Okay, special lines. Special lines. The parabola has a special line. What line is that? Do you know?
The parabola has a special line.
Yeah, it's got a symmetry line. Let me not call it special lines. Let's call it symmetry lines. Let's call it symmetry lines. Okay, your parabola has a symmetry line. It's just the line x is equal to negative b over 2a, or x is equal to p. That's it. The symmetry line for the hyperbola is a little bit more difficult. Hyperbola. The symmetry line for hyperbola has the form y is equal to x plus or minus, plus another value here. Let's call it just h for now. Okay, so it's a straight line that connects, that forms this symmetry. So that graph is done for. Let's try a new one. Okay, so these values, these lines I'm drawing here is not the x and the y axis. They are my horizontal and vertical asymptote. So this is my vertical asymptote, my horizontal asymptote, and now I've got my graph between these. So I don't care where my x and my y axis are, they there somewhere. Okay, my symmetry axis is the fact that if I fold these two, if I were to fold these two along this line, I will fold them on top of each other. Or if I fold them along this line, I will fold them on top of each other. Both cases, the gradient of the straight lines, this is a positive gradient and this has a negative gradient, but the point is the gradient is 1 to 1. Like if I'll go one step forward, I'll go one step up, or if the negative one, I go one step forward, I'll go one step down. Make sense? So the gradient is 1 to 1. The question is just where does it cut the x-axis, the y-axis, sorry. Where does my graph cut the y-axis? Now to find it is very easy, because if I have a straight line, y is equal to x plus, now I'm trying to, this can be plus or minus, I'm trying to find that. All I need to do is put a point in for x and y, a point that's on my straight line. And the point that's on both of these straight lines is that point. So that point is, remember this is my horizontal asymptote, that's y is equal to q, Remember, I'm working with y is equal to a over x minus p plus q. So this is y is equal to q, and this is x is equal to p. So h is equal to y, which is q, plus or minus p. It's actually minus or plus. Can you see why? Because if x is positive, if the coefficient is positive, then h is y minus x. If the coefficient is negative, then h is y plus x. Do you understand? That's why if this one is plus minus, then this one is minus plus. Okay, and so h minus plus q. Okay, so that's just, don't go and remember the formula for the symmetry axis. Go and find it. Okay, all you do is you choose the positive or the negative slope, and you just substitute the intersection between the vertical and the horizontal asymptote to find the rest of the formula for the straight line. Okay, so I'm not going to say anything more about that. I think let's stop there.